Okay, time for some more water flowing fun with the continuity equation and Poiseuille's law. So again, as in the last video, I have all of our equations that are listed over here to the side to give us some sense of what's going on. Our system now is a branching system. So we start in this pipe, radius 3 centimeters, length 10 centimeters. We're going to say we have fluid moving through there at 10 centimeters per second. We'll let it be water again. So water is flowing here at that rate. And then it's going to get to this region, and it's going to split into 3 paths. So we have 3 different sections that the water is going to go through. All of those sections have a radius of 2 centimeters. And then we'll say it comes back together again in a smaller pipe here, which is just 1 centimeter in radius. So we might think of this in sort of a similar light to circuits, where we have a current coming out, and then we're going to branch into 3 separate paths. Well, maybe we say first we have some resistor that represents this pipe, and then we branch into 3 separate resistors. These are not the best looking resistors. And then they come back together again, then some final resistor here, and then it will come back to our source. So we know in circuitry, whatever the current is through this section, some current I1, we know that current's going to break into 3 different pieces. And if all the resistors are the same like they are here, then we can expect that, let's say this current were 3 amps, then we would expect 1 amp, 1 amp, 1 amp. So it would break into 3 equal parts because each of those resistors is the same with the same potential difference across them. So we can expect that sort of thing here. Our analogous piece for that is the flow rate. So the flow rate is going to split into 3 equal parts. So there's a variety of ways that we could try to solve for these values. So first we could take that symmetry picture and run with that, and then see if some of our other pictures come up with consistent values. So we can't say the velocity splits into 3 equal parts. We can't say it's 10 divided by 3 in each of those sections, because the velocity is not analogous to current in our model. It's the flow rate that's analogous to current. So we need the flow rate. Q is equal to A times V. Whatever the flow rate is in this first section is going to be the same flow rate in this other section. So first we got to get that number, pi r squared, so radius of 3 centimeters. So 0.03 meters squared times the velocity 10 meters per second, so 0.1 meters per second. Get a number for that. Pi times 0.03 times 0.03, yeah, we'll do it that way, times 0.1, and we get 2.83 10 to the minus 4 meters cubed per second. So we see there's often 10 to the minus something when we look at meters cubed per second, because a meter cubed is big. It's not the greatest unit. That's why it's often better to talk about milliliters or centimeters cubed per second. But alas, that doesn't work with pressure in pascals, so we really have to be in this unit. So I'll write that up here. Q is 2.38 e to the minus 4. And then we can simply say that Q gets split into 3 in this middle section. So you have Q over 3, which is 2.38 10 to the minus 4 divided by 3. And 9.42 10 to the minus 5 meters cubed per second. And now I have to backtrack out. So given that that's the flow through each individual pipe, now I can find what's the velocity in one of these pipes. So I can just back out the calculation using Q is equal to A times V. So V is Q divided by the area. So we're going to get rid of that pi then, so if we get a round number. So 9.42 10 to the minus 5 meters cubed per second divided by area. Now we have a radius of 2 centimeters, so pi times 0.02 meters squared. So I have the 9.42, good, that's still saved here, and we'll divide that by pi times 0.02 times 0.02. And I get 0.075. 0.075 meters per second, which is the same as 7.5 centimeters per second. So we can see that, in fact, the velocity is not split into 3 equal parts that are all just a third each of 10 centimeters. It turns out you do slow down. So there is a slowing down that occurs through here. But it's not as much as a third of 10 centimeters. So first of all, you might look at that and say, oh, well, it's like, why are those velocities, first of all, slower? I mean, if we're branching into these other sections, wouldn't maybe that speed up in the sense that if you kind of narrow down, you're going a little bit faster? But what we have to look at here is that the total cross-sectional area of all of these three pipes, when you add them together, is bigger than the cross-sectional area here. So we're expecting by continuity that as your area gets bigger, your velocity has to go down. So we're seeing that that's the case. Okay, so velocity in each section, 7.5 centimeters per second. Let's see if we can get that from another way. So this way was calling on symmetry, but let's say each of these was a different radius, for instance. I don't think I'll do that to you in this class, but that is certainly a type of problem that we should be able to solve. So using continuity, let's say we know this flow rate, and this idea of A1 V1 equals A2 V2. So the A1 V1 part is just a flow rate of 2.38 10 to the minus 4 meters cubed per second. And then we're going to say that's equal to A2 times V2. Well, that's going to be N times the area of one of these pipes times the velocity going through one of those pipes. So we have three pipes, 2.38 10 to the minus 4 meters cubed per second. We have three pipes, each with an area of pi times 0.02 meters squared times the velocity. Now you might notice here exactly what we actually did before, that we had the flow rate divided by 3, just saying that, oh, this is the flow rate and you have to split it up into three parts to be analogous to what we did with circuits. Well, that 3 comes into play there, and then there's the area, so in fact this whole calculation is kind of just been done over again. I'll just re-go through it just to be on the safe side. So 2.38 10 to the minus 4, and then I'll divide by all that stuff. So 3 times pi times 0.02 times 0.02, that all in parentheses, and you get a V of 0.063. What did I do? I'm stymied on this one. 0.063 meters per second equals 6.3 centimeters per second. So I get a number that's a little bit less. I mean, it's not too far off, but it's kind of far off. I don't like that. So, not quite sure what that was, but 6.3. So we can find the velocity in that section. I keep focusing on velocity because that's an interesting piece for us to be taking a look at. Now what else can I calculate? So another calculation I can do here is, as I did in the previous type of question where I looked at, well, how much pressure does it take to move fluid through this whole system? I can think about the pressure for each one of these individual sections. But whereas before I could simply just use this resistance equation for each section when I had one piece of pipe, the narrow pipe, and then the wider pipe again, here there's no single calculation I can do for the resistance. I can't just put the numbers in and say, well, I have a radius of 2 centimeters, I have 3 of them, so I do a 3 times pi r to the 4th. The math doesn't work that way because this is not an area piece, so I can't just say it's 3 times an area because there's a pi and then there's an r to the 4th. So in fact, I'm going to have to take an approach very similar to circuits, where if I wanted to take 3 resistors that were in parallel, I had to do 1 over R1 plus 1 over R2 plus 1 over R3. I'm going to have to do the same type of idea here. So let's just take a quick look at how we can figure out these pressure differences. So we have a flow rate here, and I know this same flow rate will be true through this whole region, so I don't have to calculate that. But now I do have to get this resistance. So R being 8 eta L, 8 times eta 0.001. I'm going to trust the units at this point in the game now. 0.1 over pi r to the 4th. So radius of the 4th, radius of 0.03, and we'll square that. So we'll get a number for that. So 8 times, and I get 314 for the resistance. So smaller than I saw for some of the other numbers. I have what was it, 1600 and at 25,000. But this is a 3 centimeter pipe as opposed to the 2 centimeter pipe. So already, because of this r to the fourth principle, as that pipe gets just a little bit wider, the resistance is going to go down significantly. So 314, basically there's a pi. So the resistance here is 314. So now we need to find the resistance of just one of these pipes here, which actually I think should be that 1600 that we had in the previous video example. So 8.01, length of, I'm assuming a length of 0.1 again, and then pi times 0.02 to the fourth. Change that up, and 1592. Yeah, we'll call that 1600 value. So R for one of those pipes is 1600. So R for one of them, 1600. So we actually need to do this 1 over R idea. So 1 over R total in that section is going to be equal to 1 over R1 plus 1 over R1 plus 1 over R1. So that's 3 of them, 3 over 1600. And then the new R total for that whole section is going to have to be something less, well, 1600 over 3. So 533. So R total is equal to 533. So interestingly, the resistance is still a little bit bigger through this section here than it was through this region, but not a whole lot less. Well, actually, this is interesting. It is a bigger resistance than this one, but well, that's because the resistors were bigger than that. I'm trying to make some analogies to circuits, and I should just stop at this point. And then finally, we have this last section where we can get the resistance. So just do the 8 eta L, we call that a section 0.1. The radius is 1 centimeter, so 0.01, and that's that 25,500 that we had before in the previous problem. So again, now we can see that the total pressure that we need to push through all of these pipes is going to be the flow rate that we have through everywhere, and delta P over R. So we could do delta P times the flow rate of 2.38 10 to the minus 4 meters cubed per second, and then we would have to add up all 3 of these resistances. So now that we've put all 3 of these as a total, now each of those sections is in series with each other. So it would just be 314 plus 533 plus 25,500. So again, it's this little bitty pipe at the end that causes the most pressure need in order to push fluids through here. So just to get a final number, 2.38, and we get a 6.27. So that's how much pressure we need to get through these pipes. And we can look at each of these sections as taking different amounts of pressure. So this Q value times the 314 would say, well, how much pressure does it take just to get through this first pipe? So 2.38 10 to the minus 4 times 314. We find out that it's only 0.07. You need 0.07 pascals to get through there. And then to get through the 533, you need 0.13 pascals. You finally get through that last section, 25,500. Then you need basically 6.1, well, 6.07. So again, most of the pressure is needed to get through that last section of pipe. So this is interesting considering each different section using up a different amount of pressure. And where we see this in play in, say, the circulatory system in the body, which of course is a much more complex system than this. This is already pretty complex just for a couple of pipes and one branching. But to think about the pressure that the heart needs to supply to get blood throughout the entire body, it's basically all of these different pipes and all these different radii, all these different branchings, which all require pressure to push fluid through. So when you add all of those up, there's a certain minimum amount of pressure you need just to get blood to go through. And there's a particular flow rate the body has in mind. Plus, thinking of an enhanced flow rate when you're exercising, for instance. So you can see that each of these different sections having a different pressure. We could actually make a pressure versus position graph. Pressure versus position. And we would say that, okay, out of this total value of about 6 pascals that we need. We kind of start at the top and we drop just 0.07 in this first section. So we have 3 sections. So in this first section we drop just a little bit of pressure. So that's going through this pipe. And then we need to go through this section, and that's going to use up 0.13 pascals. So that's going to be just a little bit more. And then the last section is going to use most of it. In fact, I haven't really scaled this well because it almost looks like I've dropped 4. This last part is going to dive down and use the rest of that pressure. So really a little more of a scaled picture would look like this would look almost like a flat line. Just barely decreases a little more. And then that last section uses up the rest of the pressure. It's like using up the voltage in a circuit. It's the energy that's there. So this pressure is supplying the energy that we use. We compare that with, say, the human circulatory system. You'll often see pressure diagrams of the pressure at any given point in the body over the distance of the body, and you find that there's some kind of ringing up here where the heart is beating and there's this pulsing that occurs, and then the pressure is slowly dropping through the body. So different sections, arteries, arterioles, capillaries, they each are going to take a certain amount of pressure to push through, and you get a pressure graph that looks kind of like that. So this is where we're seeing something kind of similar in just this simple little picture, and we find that in the body as well. The pressure is dropping as you go through each section because you need a certain amount of pressure to push through the next section, the next section, the next section. Okay, there you go. A lot of problems that we did some solving for. Hopefully this gives you a better sense of how to use some of these equations to solve for different variables and to put some of these pieces together.